All right, thanks for joining us here, Space BT seminar this week. One thing that's a little bit unique, Savaria Parrish is a undergrad student here, and I was just remarking that I think this is the first solo undergrad presentation that we've had. Usually we've had undergrads come in with their own design teams like rocketry and BT or something like that. So certainly a first here for us in Space BT. Usually we have professors or graduate students, but it's good to hear from undergrads as well. So, and this week, I won't try to take too much, but yeah, using James Webb Space Telescope data and looking at atmosphere type stuff. So,
Thank you for the introduction. Hi, everyone. My name is Savaria Parrish, and I am a junior here at Virginia Tech, majoring in geosciences. I particularly have an interest in planetary science. And over the summer, I had the opportunity at the American Museum of Natural History to expand on that interest in a project with the brown dwarfs in New York City research team. We worked on a project entitled, "Can we use brown dwarfs as analogs to Jupiter-like exoplanets?" During this presentation, I will walk you through how we use brown dwarfs as celestial objects to compare to planets like Jupiter. And you might be wondering, why can't we just study those exoplanets? Why do we need objects like brown dwarfs to figure out what they are? Well, this is because in our solar system, we're able to see the planets in our night sky. So you can see Venus, you can see Jupiter, you can also see a bunch of stars as well. We're able to see those because of the proximity to us. With exoplanets, they're not close to us like the planets in our solar system are. And so when we tilt our telescope to look at them, we can only see the star. Here in this image to the right, we're trying to look at the planets, but the star's light is overpowering it. So we can't actually study those exoplanets. We can only study the star. This is where brown dwarfs come in. Brown dwarfs are the middleman between a planet and a star. It's kind of like a hybrid. And to get a better understanding of what this means, I'll explain to you the formation processes of a star, a planet, and how it compares to brown dwarfs. Because it's October and it's kind of Halloween season, I thought I'd explain it with a witch's brew or a concoction. So in order to make a star, you need a bunch of hydrogen and helium. All of this gas needs to be around 10 to the 29 kilograms in mass. This is so you can have gravity. The gravity condenses that large gas cloud so that it can become a star. When it does that and collapses in on itself, it becomes to a temperature of around 15 million degrees Kelvin. This temperature is needed so that nuclear fusion can start and the star can be born. A star burns off of nuclear fusion, and that's how we get the brightness of it. So if you do all of these steps, congratulations, you have a star. Get any of those steps wrong, congratulations, you have a brown dwarf. Now, I had to put this image of a smiling brown dwarf because all of them were all sad because they're failed stars, but they have other uses as well. With planets, however, they form a tad bit differently. Planets form as the discretionary disk of a young star. So when the star is forming and it's becoming a star, it has a disk around it. The terrestrial planets tend to form closer where all the rocks and materials are, while the Jovian planets tend to form where all the gas tends to coagulate on the edge. This is how planets are formed. With brown dwarfs, they have similar characteristics of both planets and stars because of the way they form. Their similarity to planets is they have similar size, similar temperature, and they have cloud structures, sort of like Jovian planets like Jupiter, with the large storms and have convection, cloud convections and weather patterns. They're also similar to stars in the sense that they have the same formation processes, and they faintly glow as well. Think of it like a bonfire, for example. You have the big ball of fire that represents the star, and you have the little coal that's there as well. The coal is dark and it's glowing, but it's not glowing as immensely as the fire itself. And the planets would be like the little embers that come off the top of the fire. So how can we study brown dwarfs? We study them using telescopes. I studied my brown dwarf using the James Webb Space Telescope. And on the James Webb Space Telescope, there were two instruments, the near-spec instrument and the MIRI instrument. To understand this better, we study those brown dwarfs using light. The instruments collect the light and we're able to see their temperature and what they're made out of. This works this way. When we collect the light, there's something called a black body spectrum. we have the spectral energy distribution as opposed to wavelength. Where that light peaks, we can see what temperature it is. The brighter something is, the hotter it is. And so as it peaks, it tends to move over to the right of the diagram. So hot objects tend to be in the ultraviolet, and as they cool down, their peaks move over to different wavelengths. And as it moves over, we can see that cooler objects are in the infrared wavelength. We can also zoom into this and see that at certain wavelengths, there are certain dips within it as well. These dips correlate to specific elements or molecules, and that's how we can figure out what it's made out of. Now back to brown dwarfs and their classification system. As I told you before, brown dwarfs are the hybrids between planets and stars. They're also divided into three types, L, T, and Y. This is because as you decrease in temperature and become more closer to a planet-like structure, you expect different spectral and temperature resolution types. My project, for example, focuses on that LT transitionary boundary. The LT transitionary boundary is important because of the different subtypes that are within it. For the L-type brown dwarfs, they're characterized by having sandy atmospheres or sandy clouds within their atmosphere. But as you transition to the T brown dwarf, as you cool down in temperature, they're characterized by not having silicate clouds in their atmosphere. This happens through a process called sedimentation. As you cool off, the sedimentation starts to happen. So think of silicate atmospheres as sandy or grainy atmospheres. As the brown dwarf tends to cool, those silicate clouds tend to decrease and go towards the bottom. But then you get other elements such as methane, or if you go down to Jupiter, you get something called ammonia that we can see in their atmosphere. This is where my project comes in. I studied the brown dwarf binary system WISE 1049AB. It was discovered in 2013 by Dr. Kevin Luman. It is made up of two brown dwarfs that were set to form in the same disk. And because they're set to form in the same disk, they should have similar characteristics. They're important to my project because they are a catalyst within the LT transitionary boundary. We have the A component, which is a little bit bigger, and it is an L8 brown dwarf. And we also have the B component, which is a little smaller, and it is a T1 brown dwarf. If we go back to those spectral types, those little subtypes are right in the boundary of each other. So going back to the spectral energy distribution that I was talking about, when we collect the telescope data, we're able to see where it peaks and also those dips within it. The focus of my project was to identify the main chemical features within the brown dwarf binary system and also compare those observations with atmospheric models. For the A component, we found that we should see those silicate materials in the A component since it is an L8 brown dwarf. And in the B component, we found that there are no silicate materials within it as expected since it is a T1 brown dwarf. We also saw that because the A component is a little bit warmer, it doesn't condense some of those molecules as much. But T1 brown dwarf, you can see the H2O and methane bands are condensed, where here it's just water bands. It's not condensed yet because it's still warm and not cool like the T1 brown dwarf. And here's a better image as well of where those differences occur. The second focus of my project was to compare those James Webb Space Telescope observations to atmospheric models. And we do this because we want to improve our atmospheric models. In order to do this, we need to measure them to the real thing to figure out how can we use these models to accurately predict the things we want to look at. We also now have the ability to explore cloudy atmospheres with our models. Previous models didn't have clouds in their models, but they had the elemental basis of it. To do this, we use the Sonora Diamondback models. The Sonora Diamondback models are brand new models that incorporate cloudiness into their code as well. We took over 30,000 synthetic spectral combinations of gravity, metallicity, mass, and cloudiness. So here's an example of all of them listed as here. In this graph, I have them plotted as well, and you can see some of that black body radiation as well too. So we have the model that would be 900 degrees. You would expect to see a spectrum line here. as you increase in temperature, you expect to see different combinations and different dips of the different lines within the model. To bring this back to my project, we're trying to figure out which of these synthetic cloudiness models best accurately represent the actual observed spectra. To do this, we use the Spectral Energy Distribution Analyzer, or SEDA. SEDA is a code that was developed by my advisor, Dr. Genaro Suarez, and it helps to find the best fit synthetic spectral model. It does this by using the chi-squared statistical method. Yeah, it does this using the chi-squared statistical method. And essentially what that is it overplots the 30,000 synthetic spectral models over top of the actual observations. And within those observations, it figures out which one has the least amount of error or which one has the closest match. Here we found the best fit models. So in the orange, we have the actual best fit models that out of the 30,000 synthetic and cloudiness models. And in blue, we have the actual observations from the James Webb Space Telescope. You can see that there's a little bit of differences within these two. And this means that we need to better our models for our cloudy atmospheres. Essentially, it's a little bit more detail. We found that in the near infrared, for component B, it kind of best matches here than it does here. We also found that there was the most discrepancy here near the mid-infrared. To figure out, was it the James Webb Space Telescope or was it our models that were inaccurately depicted here? We compared the James Webb Space Telescope data to the IRTF, or Infrared Telescope Facility in Hawaii, and we compared those two to figure out, okay, is it the models or is it the James Webb Space Telescope data? As you can see, we pointed the IRTF and the JWST telescopes to the same objects, and we got around the same type of spectral line. And so because we got around the same type of spectral line, we know that we can trust the James Webb Space Telescope data and that it's actually our models that aren't actually depicting it well. In the red, you do have the IRTF data here in the near infrared. And the really cool thing about it, even though that it's missing in the mid infrared, that is the power of the James Webb Space Telescope, because we didn't have a telescope that measured in the mid infrared. And now we do. And so we have a plethora of data points here as well. So now that we know that we can trust the James Webb Space Telescope, we're able to identify the differences in those atmospheric models a little bit better. Because they were formed in the same disk, they should have the same metallicity, which is essentially the elements that it's made out of. It should have around the same gravity, and it should accurately depict the temperature well. The best fit model says that for the A component, it should be around 1100 degrees. That's not true because we know that it's around 1300 degrees. So that needs a little bit of help. We also have the gravity here, or the specific gravity is at a level of 31, and the metallicity is at plus 0.5. For the B component, as I said, they should be a little bit similar. We have that the best fit model found was around the same temperature of 1100 degrees, which is sort of close because the B component is actually at a temperature of 1200 degrees. We found that the gravity was very different, and it shouldn't have been that different, but it was found that it was. And we have a metallicity of negative 0.5. We know that these models need a little bit of correction in them as well, because the metallicity should be around the same as well as the gravity should be around the same. So for our future work, we plan to constrain the parameters to have a similar metallicity and gravity. We plan to compare it to other atmospheric models, and we plan to use the James Webb Space Telescope for other objects and other brown dwarfs as well. So to answer the question, can we use brown dwarf atmospheres as analogs to Jupiter-like exoplanets? The answer is, we already do. Thank you. Yeah, if you have any questions.
Yeah.
Hello.
So, hi, great talk. I did planet astrophysics as my undergrad, so this is bringing back a lot of things that I learned back in the day. But I do have one question for you. So I noticed in the beginning of your in your presentation, you were talking about how brown dwarfs are different from planetary bodies and sun and star-like objects.
Yeah.
What along the way creates a brown dwarf? Because from my
Mhm.
understanding, I thought it was because there wasn't enough material in the accretion just to create it, but it seems like there's more interactions that might have disturbed its evolution to one of the other objects. So can
Yeah.
you talk more about that? 'Cause I
Of
don't.
course. So brown dwarfs, they would be specifically known as failed stars.
Yeah.
And essentially with the brown dwarf, they don't get big enough to create nuclear fusion. And so that's what causes it to fairly glow, but it doesn't burn like a star. And because it doesn't burn like a star, it's not technically a star. It's
So-
very dim, it's a brown dwarf.
So does that correlate to not having enough material?
Yeah.
Okay.
Yeah,
Okay.
so essentially you're supposed to have a lot of hydrogen, a lot of helium, a lot of gas to be able to collapse in on yourself and have enough gravity to support nuclear fusion. And essentially with a brown dwarf, it collapses in on itself, but not at the mass needed to sustain nuclear fusion. So it doesn't have enough material to start nuclear fusion and enough mass to do it. So it glows a little bit, but not faintly. Think of like the charcoal analogy and how charcoal would glow, but it's not like fire. Yeah. You're welcome.
Oh, yeah, I could do this all day. That's great presentation and great research.
Thank you.
The first cool thing, right? Those brown dwarfs can't be separated by too much, so I was surprised that James Webb and
Mhm.
the other infrared telescope can distinguish between the two.
Yeah, that was actually a really interesting part of the project as well, because there's been 3 cycles, I think they're on their 3rd cycle now. The first 2, they couldn't distinguish between the 2 fluxes of the 2 brown dwarfs. So like you could get this side of the brown dwarf, you could get this side of the initial brown dwarf, but that in between bit, the fluxes were kind of combined. And so they've had to study it using 3 cycles of the James Webb Space Telescope to try to figure out like how to distinguish between them.
Okay, I just gotta believe that's a rare thing. That-
It's really,
That's basically a solar system.
yeah,
Like, even if it's a 2-star solar system, if you look at it that way,
yeah,
but that we can isolate them. I can't think of any other example, at least
Yeah.
not that I'm an astronomer, but.
yeah, and it also helps because the brown dwarf binary system is 2 parsecs away, meaning it's actually the closest and brightest to us. And so if it was any further, we wouldn't be able to try to distinguish between the 2 objects. But because it's so close to us and because it's so bright, we're able to use the James Webb Space Telescope to do that.
It must be possible that there's a planet.
Mhm.
Well,
Yeah.
You know,
Yeah,
you
of
see
course.
any evidence of that?
So I could talk about this all day. Within my brown dwarf, I'm not too sure if there is a planet, but within detecting exoplanets, although we can't like see specifically their light, when they're orbiting around their star, they tend to block out some of the light of the star. So if you were to record a star, let's say for 2 days, you'll see that within the video, the light tends to dim like as the planet goes around it at specific locations. And that's how we know that the exoplanet is there. It is being orbited by something because it's blocking the light in a type of orbit, but we can't actually see it because the sun tends to overshine that planet. So we use the brown dwarfs as analogs to it, to what those planets might look like or what those Jovian planets could look like.
A couple more and then you can shut me up. When you use the model
Yeah.
and you get temperatures of 1,000 degrees,
Mhm.
that's pretty warm. Is that near the surface? Because you have methane and water and things in the atmosphere.
Yeah.
That doesn't sound compatible with 1,000 degrees.
Yeah, which is really interesting as well. It's a question that I had for my advisor. I think we're still trying to figure out with the Sonora Diamondback models, what exactly they mean by that as well. There's a group that actually works on the Sonora Diamondback models, and because of our project, they're improving the way that they're doing the models. And so once they're done improving the models, we're gonna retest them on the James Webb Space Telescope data.
Okay. And getting the gravity of 3,000 or 300
Yeah.
or less,
Yeah,
that sounds wild.
that does. But let me see.
What's the real answer?
Let me see.
I assume we know that.
Yeah. Oh, wait, there we go. Yeah. So because we know the temperature and the metallicity should be that of close to the sun, so it should be around 0 metallicity. instead of surplusing or I forgot what the other one is, opposite of surplus. But essentially, the temperatures we know for a fact are 1300 degrees Kelvin and 1210 degrees Kelvin. But the gravity, I'm not too sure I know off the top of my head. I'd have to look more into the research paper behind it. But it's not supposed to be either of those two numbers. They're kind of like far ends of the spectrum a little bit. So yeah. But yeah, these are what the Sonora Diamondback found to be the best fit models. If we go back a little bit, you can see that each model has a specific temperature, a specific gravity, and a specific cloudiness that goes along with it. And so it goes through all 30,000 of those combinations, compares it, and plots what it finds. And we can obviously see that we need a little bit more work on those atmospheric models, but luckily our work is helping them out with developing that.
Yeah, it's very cool.
Thank
It
you.
surprises me with the gravity so different in those two models.
Yeah.
That could look pretty similar.
Yeah, that's what surprised me as well. I was looking at it, I was like, are you sure this is right? Do we need to rerun it again? So yeah, but it's these are new models that incorporate clouds into the atmosphere. Before then, we had models that didn't encapsulate clouds into their atmosphere as well. And so these match up a little bit better now.
So when you say clouds were incorporated into the model, do you have an idea of how that was done? Because from my understanding, because there's different cloud types that
Yeah.
might, depending on how thick or thin, or
Yeah.
what the particulate matter that's causing water to condense on it, like how would that be incorporated into the model itself?
I'm not too sure on that specific question, but I know with the cloudiness models, there were different levels within it. And so,
So that's just more just like percent blockage kind of a thing?
yeah,
Okay.
because the clouds kind of block out some of the light that would come up from the brown dwarf because it glows, but now it has this sheet over it. And so there's different levels. I think it was a scale of 1 to 10, 1 being most cloudy, 10 being not as cloudy. And so it would do that. I'm not sure. I'd have to talk more about it with the Sonora Diamondback group about how they're characterizing each of the cloudiness models and how that would look. Yeah. Yes.
So for this brown dwarf in particular, was the cloudiness kind of consistent, or like visually from what you've been able to see,
Yeah.
was the cloudiness kind of consistent, or did it vary depending on what the equator versus the north and south poles?
It would vary a little bit. So essentially, this is actually a really good question that Hanaro, my advisor, is actually working on. Depending on what angle you're viewing the brown dwarf at, you're going to get something different with the cloudiness because the clouds move. So because the clouds are rotating and the clouds are moving, depending on the angle you look at it, it might not be as cloudy, or it might be cloudy when you look here, and it might be not as cloudy if you look here because of how like the convection around the brown dwarf is looking. Sort of like Earth, if you're looking at a specific area on Earth, there could be clouds at one moment and then clouds not there at another moment because the clouds are moving as well.
Oh,
So, yeah.
that's cool.
Have you tried taking that model and just applying it to Jupiter itself?
No, I haven't. That's actually a really good idea now that you say that. But I haven't particularly used the model on Jupiter itself, but that does sound like a really good idea.
I'm not from this department, so I can't really ask any riveting questions.
Yes.
I'm from the biomedical department, so it's quite a way away,
Yeah.
but I can like hear your love of the topic, just like in every word you say. I guess my question was like, what was the most interesting part of the research to you?
Ooh, okay. I have two answers to that. One would be working, like one pertaining to the research and one not pertaining to the research. One would be actually, let me see, actually working in the American Museum of Natural History. That was probably one of my favorite things. Like the building is so advanced. We got to see like different things on the tours as well. They took us to a locked part of the library in there that's like not public to anybody, and I got to see some really cool stuff. I think I also worked with Neil deGrasse Tyson. We didn't work together, but we worked in the same building. And so he actually served us wine at the end of our presentations and stuff. So that was really fun, like meeting him, getting a picture and everything. So that was like the actual work experience of being in the museum, seeing actual data that like the normal person just wouldn't have access to, I guess you could say. And then the actual part of the research that I found most interesting and most rewarding was learning how to code. I've had a little bit of coding experience before, but actually being able to see my development, because we use Jupyter notebooks. I'm not too sure if you all are familiar, but it's essentially kind of like an IDE and it keeps track of all of your code that you've been doing in. And I watched me go from print this to actually developing like actual loops and stuff to help me kind of like plot out my figures and everything. I could actually show you if you really want me to. Because I keep it as kind of like my prized possession of just watching my progress. And I think that was probably the most inspiring and rewarding part because it was really hard in the beginning, but then seeing my progress towards the end, I'm like, oh, wow, I can do this. This is nice. So yeah. I think something that I also figured out is I figured out myself a little bit more. I figured out what I'm interested in learning more about. And I also figured out that I don't like living in New York City and I don't like taking public transit. Learned a lot on that one. Definitely. It's like, oh, commuting 30 minutes. And it's like, I don't mind the commute, but I'd rather be alone in a car on the commute than the crazy people of New York City. I'll tell you that much.
Just in-flight entertainment is what I call it.
Yeah, you know, off the record, I'll tell you the things I saw, but while we're still on record.
One kind of more technical is, it was interesting to see, and one thing you're saying that the disparity between the model and what the data you took was actually a spot where, the place in Hawaii
Mhm.
can't record.
Yeah,
Is that that seems almost expected where a place, that the model might be trying to guess, is that, I guess that's what's going on, is it's trying to
Yeah.
guess because.
we
there's
don't
not a
have
lot of-
data.
Yeah.
Yeah,
Okay.
so that's like exactly the point. That's really cool because the MIRI instrument is a brand new instrument and it's only on the James Webb Space Telescope. And so it's the only instrument that can measure in the mid-infrared. And so now that we have that instrument, this is like the data that we get from it, but we would definitely need to develop more instruments to kind of verify that mid-infrared data that we're collecting.
Yeah, I guess I was just gonna ask if you knew anything and presented some of the model, the SEDA,
Mhm.
or SEDA, that, is that sort of the work that's going on developing and
Yeah.
expanding?
Yeah, actually, Hanaro, he's a really great person. I definitely recommend, like, I'll put his contact information there. But he's working on the SEDA package. And also within the SEDA package, there's like different computer models like Windows, Mac, Linux, for example. And I also had a hand in helping kind of develop the code for my specific computer because we had two separate computers and we figured out, oh, it's a backslash here and a forward slash on this type of operator. So I had a hand in that, but he's actually talking with Beth Biller, who was actually in charge of this cycle of recording the Y1049 AB binary system. And we're all in cahoots with the Sonora Diamondback model people as well and trying to figure out exactly what we're looking at and how we can kind of further develop it a little bit more. Thank you.
I think it's fascinating that
Mhm.
his question, I think you can go a step further, right? Because we do have those observations of Jupiter. Those models almost certainly
Mhm.
have some basis in
Yeah.
Jupiter because we have all that information and
Yeah.
composition and all that.
Yeah.
But if there's a region of the spectrum where the models are not working,
Mhm.
then there's something that it's just not working in the atmosphere,
Mhm.
based on what we'd expect from this solar system. So there's
Yeah.
really some cool questions there that hopefully will get answered.
Yeah, there's actually, we looked at LT transitionary brown dwarfs because of the development of the silicate clouds in the L and then not seeing those clouds anymore in the T. But, excuse me, why brown dwarfs are most similar to Jovian planets because of their temperature. They tend to be a little bit more on the temperature scale of what we like might expect or might see. And so I think we're gonna try to see if those models actually correlate with Y-type brown dwarfs now that we know like it actually proves the silicate and non-silicate of the LT transitionary boundary, we can trust that it'll look at the boundary between a Y-type dwarf and a Jupiter, an actual Jupiter-like planet.
Are you gonna continue this yourself or?
Yeah, we're actually, I'm gonna propose the idea to him, mainly because like funding and everything like that. I was funded by the National Science Foundation and not the Brown Dwarfs in New York City Research Group. So that would be like an actual thing that I'd have to discuss with the team on continuing it.
Fascinating.
Thank you.
I have a question.
Mhm.
So when you said that the temperature was supposed to be 1300 or 1210
Yeah,
Kelvin, but you obtained 1100.
yeah.
So that expectation, was that based on observed data, or
Mhm.
is it for how the model is usually supposed to predict?
Yeah, so let me go back to it a little bit. See, so the model itself, I believe the Sonora Diamondback models are created off of another object that's not Y1049 AB. And so the line spectrum itself is saying that the 1100-degree model or synthetic model best matches the actual observed data. But we know that the temperature shouldn't be 1100 degrees. And so now that we know that it shouldn't be 1100, it should actually be 1300 or 1200 in this case, we can actually edit those atmospheric cloudy models to help further match it and further better those models to actually, when we have observed data, to keep comparing it to the actual thing to see if it's actually predicting right.
Okay.
But don't both those numbers, the 1300 and 1100, come back from the spectra?
Yeah, so that's like the really cool thing about it as well, is even though it is off by a little bit, it's still not as a big of a difference between like the two gravities, how they're on opposite ends of the spectrum. 1100 is pretty close between 1300 and 1200. And another reason why it might have given the temperature of 1100 for both of these is because they are so close together and there's only like a 50-degree kind of difference between the 1300 and 1250 atmosphere, that it probably couldn't resolute or like find the resolution between the two, and so it gave the same temperature for the same two, or for the different two.
Other questions?
I really want to thank you for giving this presentation.
Thank
And,
you.
You just got accepted to give this talk at a conference,
Yeah.
right? It's okay, I want to say the Space BT is partially supporting that.
Mhm.
We really appreciate you doing that.
Thank you so much. So yeah, thank you guys. I'll also be available after the talk. If you have any more questions, or for those who came in late, I don't mind like repeating it a little bit more again. And then, yeah, scan the code, connect with me on LinkedIn. Thank you.
Thank you very much.
Thank
Uh,
you.
And as far as Space BT seminars, in 2 weeks, I'm actually gonna be out of town or out of the country, so we'll hear in 3 weeks from Dr. Rob that's out of our Super Army. See you in 3 weeks.
Thank you.
And thank you all.